Hello students. In the previous video, we discussed about some valency bond theory questions as well as valency bond theory techniques also. Right. So today I'm going to explain you in this video about crystal field theory. Right. Many students have difficulty while understanding this concept, crystal field theory, and little complicated theory also. So let us discuss about crystal field theory. Right. So very important theory. Listen carefully. Crystal field theory. It's mainly about splitting of d orbitals. It is mainly about splitting of d orbitals. So what is this splitting of d orbitals? That we will learn here. Right. This theory has made very two important assumptions. Before we go into the detailed study of this, let us see the assumptions of this theory. First assumption, what this theory says, that the metal ligand bond, this theory said metal ligand bond is purely ionic, which means it is 100% ionic bond. Let us understand the meaning here. They mean to say, if you take a complex, let us say tetrahedral structure, this is Ml4, right? Here the bond between metal and ligand, they are saying the ligand will completely transfer the electron to metal, and here the metal actually possesses positive charge, let us say plus n number, and the ligand is having something minus x charge. So the bond between metal and ligand is like a charge, it's a bond between opposite charges. So that is what they call the bond between the metal and ligand is ionic bond. Got my point here? I repeat, this is the first assumption. Assumption number one. What they said is, if you take any compound, here metal generally possesses positive charge and the ligand possesses negative charge mostly. Here the bond present between positive and negative charge is ionic bond. So that is what they said, the bond between metal and ligand is 100% ionic bond. But actually that is wrong one, because if you take any bond that is exactly not ionic bond, there will be some covalent bond, because this positive charge will bring the electron towards inside, so there will be some sharing of electron also. Got my point here? I'll explain here. If you take any positive charge, A plus and B minus, it cannot be 100% ionic, because the positive ion will bring the electrons towards the middle side, and it has a tendency to form covalent bond. So that means no bond is 100% ionic or purely ionic. So but these people ignored the covalent nature. There will be some covalent nature, but this crystal field theory ignored the covalent nature of the bond. Got my point? I repeat, that's why this theory is also known as electrostatic model. This crystal field theory is also known as electrostatic model, because the ionic bond is also known as electrostatic bond. Ionic bond is also known as electrostatic bond. Okay, first point is that one. So bond between metal and ligand is what they assumed is like a bond between opposite charges. So it is like acting as ionic bond. That is what they assumed, and they ignored covalent bond. So but as we know, no bond is 100% ionic. So this point I am going to explain in the drawbacks. This is the first assumption, and I will explain this point in the drawbacks. Second point, what they said, ligands are of two types. Ligands are of two types. What are those two types? Anionic ligands or negative ligands, you can say, and the other one is neutral ligands. Positive ligands are very rare. anionic ligands are considered as point charge. They said anionic ligands are point charge and neutral ligands are behave like a dipole. So what is the meaning of this? Let us see. Suppose there is a metal and here ligand like let us say Cl minus. So this theory says this ligand Cl minus act as point charge. It is acting as point charge, and as this is approaching towards metal, as this Cl minus is approaching towards metal, so there exists repulsion between electron of metal and electron of ligand. So there exist repulsions between electron of metal and electron of ligand. That is what they said. In the case of negative ligand, suppose if you take a neutral ligand, suppose there is a metal and a neutral ligand, let us say water, and water is acting as a dipole. So you can say OH minus partial negative charge and H plus. So this is acting as a dipole. So this is the metal, and when this ligand is approaching, here ligand act as dipole. That is what they said. Again, when this ligand is approaching towards metal, again there exist repulsions between which one? Electrons of metal and electrons of ligand. So ultimately they mean to say whether you take ligand as a point charge or ligand as a dipole, so there always exist repulsions, but repulsions will be more in which case, that you have to think. Since it is a ligand, anionic ligand, so this would create more repulsions. This would create more repulsions than a neutral ligand. Got point here? So I repeat once again, assumptions. There are two assumptions here. In the case of metal ligand, the bond is present between the opposite charges. Opposite charges bond means ionic bond. So they said metal ligand bond is purely ionic. Clear? Second point, ligands are of two types, negative ligand or neutral ligand. If there is a negative ligand, so it will act as a point charge, and when the ligand approach the metal, there exist repulsions between electron of metal and electron of ligand. If ligand is dipole or neutral one, it will act as a dipole. There also repulsions will exist between electrons of metal and electrons of ligand. So ultimately there will be repulsions between electrons of metal and electrons of ligand. Got my point here? So here if you can see metal and here ligand, there will be electrons in the metal, there will be some electrons in the ligand. So electrons of metal and electrons of ligand always repel with each other. That is the main assumption of crystal field theory. There are two important assumptions. So I hope you understood it. So rewind the video in case if you have trouble in this one. Now, based on that, how splitting will happen, we will see. So we have a different concept, splitting of d-orbitals. But before I go for splitting of d-orbitals, let us discuss the shapes of d-orbitals. This is the one concept which is necessary. D-orbitals, you know, there are 5 d-orbitals. How many are there? 5. What are the names of those 5? dxy, dyz, dxz, dx square minus y square, and dz square. Here the shape of dxy, double dumbbell, you all know that. Double dumbbell between x-axis and y-axis. This is double dumbbell between x-axis and y-axis. It is the name of dxy. And dyz, it is double dumbbell between y-axis and z-axis. Axis names I am changing. Now dzx between x-axis and z-axis, dzx, and dx square y square, that is presenting on x-axis and on y-axis, and last dz square, which is presenting on z-axis, only on z-axis as well as around the center. So here we can see one thing, these three dxy, dyz and dzx were lobes. Lobes means these dumbbells, these are called as lobes. So lobes are present between axes, lobes present between axes, and in these two, that is what dx square y square and dz square, in these two lobes present on the axis, on axis, so keep it in mind. So the here lobes are present between the axis and here lobes present on the axis. The group of these three, these are three degenerated orbitals, so the group of these three is called as T2G. Why do we call T2G? T stands for triple degenerated orbitals. So 2 is a different symbol, so T2G, G stands for generated, so triple degenerated orbitals, and these two orbitals are called as EG. E stands for double, so there are two orbitals, so double generated orbitals, so double generated and triple degenerated. G stands for Gerard, also people say Gerard. Now, so totally d orbitals are classified into two types, d group of T2G and group of EG. In T2G, dumbbells present between the axis, and in EG, dumbbells present on the axis. Clear? Now we will see how the d orbitals get splitted in octahedral system. So heading is splitting of d orbitals, splitting of d orbitals in octahedral system. First you have to understand what is octahedral system, then only you will understand this one. In octahedral system, the hybridization is D2sp3. Hybridization is D2sp3. Here 2 points are very important. As the first one is structure. Structure is octahedral, which means here metal with 6 ligands. So you all know what is octahedral structure. So this is octahedral structure. Here what is the bond angle? Bond angle here, everything is 90 degrees. Bond angle is 90 degrees, means all are perpendicular to each other, which means if I consider this one as x-axis, this one as x-axis, this one will be y-axis, this one will be z-axis, because all are perpendicular to each other. So here in octahedral system, that is a main point. In octahedral system, ligands approach the metal in which way? Along the axis. That is the point number 1. So which we have to understand. So without understanding this, you cannot go further. Ligands are approaching along the axis. Now here you see metal have d orbitals. Metal is having d orbitals, dxy, dyz, dzx, dx square minus y square and dz square. Here there will be repulsion. As we have studied, there will be repulsions between the electrons of ligand and electrons of metal. But metal all electrons will not experience same repulsion. Here EG electrons were dumbbell on the axis. Ligands are also coming along the axis. Here dumbbells are also presenting on the axis. So they will face more repulsions. Got my point? I repeat once again. Here the ligands are coming in which manner? Ligands are approaching in which manner? Along the axis. And in the metal, the dx square y square and dz square. That is what we have drawn the figure on the axis. This is the dx square minus y square and dz square. Here the ligands lobes are on the axis. That's why these orbitals of metal experience more repulsions from the electrons of ligand. Got it? I'll write here so that you will understand more better. So the d orbitals in which dumbbells, or you can say dumbbell or lobes, dumbbells present on the axis. What are those d orbitals? That is dx square y square as well as dz square experience more repulsions. These are very key points. Experience more repulsions. Because why they are experiencing more repulsions? Because ligands are approaching along the axis. Ligands are coming along the axis and these EG orbitals also presenting on the axis. So there will be more repulsions between electrons of metal and electrons of ligand. Now I will explain with a figure. So let us see, these two are key points. Here metal atom is alone. Let us say metal atom is alone. So all its d orbitals have same energy, which we call degenerate. Here all the d orbitals are degenerated orbitals. Degenerated means same energy. All orbitals will have same energy. This is the, let us say, energy increasing order. Now when you add ligands, all the ligands first they approach in a spherical manner. All the ligands are equally surrounding the metal from all directions. So their ligands are approaching in a spherical manner. So because of the repulsions between the electrons of ligand and electron of metal, the energy of d orbitals is increased, but still they are degenerated because ligands are approaching in a symmetrical manner. You can say symmetrical arrangement. Now when octahedral structure is formed, so you see what is happening. So ligands now they approached along the axis. Finally along the axis. That's why which one will experience more repulsion out of these? EG will experience more repulsions. EG means dx square y square as well as dz square will experience more repulsion, and T2G will experience less repulsion. That is this one, dxy, dyz and dzx. This is what I said, splitting of d orbital. I said in the beginning of the topic, splitting of d orbitals in octahedral system. How they have splitted, you just see. Now here the middle point is known as barycenter. So means energy barrier. So above the energy level is increased by 0.6 del O. The below the energy level is decreased by 0.4. So you can write minus 0.4 del O. Right, minus 0. Del O, that is for T2G orbital, and this is for EG orbital. So if they ask in exam, you have to draw like this. And here the energy gap is not equivalent. You see, it is 0.6, it is 0.4. So the gap little bit it is more, and here the gap is little bit less. These are the very sharp observation point, and these all things should be above to this one. This is the degenerate orbital when metal is alone, so its energy will be very less. So this energy will be little bit more. So here, so what can we write? The energy order of d orbitals in octahedral system. Yes, you tell me which one having less energy? It is dxy is equal to dyz. Both have same energy, which is equal to dzx. But these all three will have less energy than which one? Dx square y square is equal to dz square. This is the MCQ question regarding energy order of splitting orbitals. Now here there will be some energy difference between these two, T2g and EG. That energy difference is known as crystal field splitting energy. I use abbreviation CFSE, crystal field splitting energy or crystal field stabilizing energy. But in the presence of ligands, if the ligands are not there, there is no difference between all these energies. Here energy gap is there. So definition, what can we write? Let us see. Now CFSE, what is the full form of CFSE? Crystal field splitting energy definition, which some people say stabilizing energy also, whatever you like you can say. So what we have said, the energy gap between or energy difference between T2g and EG orbitals, T2g and EG orbitals in the presence of ligands, in the presence of ligands is called as crystal field splitting energy. Now this, based on this splitting energy, we have so many things. I'll draw the figure once again. I am drawing only half figure. This is the symmetrical distribution of ligands, and now they are getting splitted. What will come here? T2 EG orbitals, and here this is T2g orbitals. T2g orbitals, this is the barycenter. Now suppose you have a D1 system. Suppose now the energy gap, this is what I said, crystal field splitting energy, it is a del O. If del O is very high, then the electron will definitely pair in the lower level. Suppose if I say D1, suppose I have any compound which is having D1, one electron. So one electron definitely will go to which level? T2g1 and EG0, because as per Hund's rule, Aufbau rule, electron will go to lower energy level. Suppose if I have any D2 system, if I have two electrons here, now what will happen? The two electrons will come in T2g. So you can say T2g2 EG0. If I have D3 system, third electron will come to T2g. So you can say T2g3 EG0. But now in the case of fourth electron, or I can say D4 system, the fourth electron may pair up in the T2g orbital or may go to EG. There are two chances, two possibilities. Possibility number one, that is, if energy gap is very big, then electron will not go to EG, it will definitely pair up here. So that is what I say, if energy gap means del O is very higher than pairing energy, means energy needed for pairing of electron. So del O is very high, so electron will not go over there, instead it will pair here only. So in that case D4 can be written as first electron, second electron, third electron, fourth electron here only. So you can write T2g4 EG0. 0. But in the case of case 2, in case 2, if the energy gap is less, let us say, if energy gap is less than pairing energy means energy needed for pairing the electron. Here pairing the electron require more energy, so instead electron will go to higher level, that is D4 can be written as T2G3 Eg1. Got my point here? For fourth electron, suppose if you think, sir, you give me another example. Yes, I will give you another example. Suppose fifth electron, or I can say D5 system. Now you tell me what happened in the case of D5 system. Case 1, suppose if energy gap is very high than energy needed for pairing electron. So electron 1, 2, 3, pairing will be done there itself. So what can we write? D5 is equal to T2G5 Eg0. But here, if energy gap is less than pairing energy, it means the energy gap is very less, so electron will automatically, fourth electron will go here and fifth electron will also go there. So what will come? D5 is equal to T2G3 Eg2. So like this we have to write the d orbital distribution. In examination they ask write the d orbital occupation. They ask write the d orbital occupation, so we can write d orbital occupation like this. Now let us make a table so understand it more clear. Now table, in the case of strong, first of all d system, then strong ligand means the energy gap is more than pairing energy, and weak ligand, the energy gap is less than pairing energy, right? So we can make a table for all D1. Suppose you have only one electron, so where it will go? It will go to the T2G orbital, so T2G1 Eg0. So same, whether it is a strong ligand or weak ligand doesn't make difference. I hope you are getting my point. Okay, so if you have any trouble, you can ask me in the comment box. I will make another video also. T2G2 Eg0, here also T2G2 Eg0, so there won't be any problem. D3 T2G3 Eg0, same here T2G3 Eg0. Now the problem comes from fourth electron. If the ligand is strong, the electron will be paired there itself. So you can say T2G4 Eg0 if strong ligand, and if it is a weak ligand, to T2G3 Eg1. Now D5, if it is a D5 system, the fifth electron will go to T2G5 Eg0, and if it is this T2G3 Eg2. Got it? So you have to make the big list because it can be asked in any exam. Suppose a D6, what can you write? It is a T2G6 Eg0, and here T2G, because there are 3 orbitals here, 2 orbitals here, 6 electron, 1, 2, 3, 4, 5, 6. So what can we write? T2G4 Eg2. You know it very well. D7. So 1, 2, 3 is a strong ligand, so pairing will be there. 1, 2, 3, 4, 5, 6, 7th electron will come in the Eg level. So you can say T2G6 Eg1. And here you tell me what will come. 7 electrons. 7 electrons, what will write? 1, 2, 3, 4, 5, 6, 7. So it will be T2G5 Eg2. Now D8 system. D8 will be T2G6 Eg2, and here T2G6 Eg2, and D9 it is a T2G6 Eg3, and here it is T2G6Eg3, and finally D10 it is a T2G6 Eg4, and here also T2G6 Eg4. So difference, where did you find the difference between strong and weak field ligand? Strong field and weak field ligand, you will find the difference from D4 to D7. Before and after this, it doesn't make any difference whether it is a strong ligand or weak ligand. The orbital, d orbital occupation is remaining same. So here you will see the difference. Got my point here? Yes. So now next one, we have to calculate the energy. How to calculate the crystal field splitting energy? Crystal field splitting energy formula, that is, what is the energy of this one? We have drawn here. So here the energy of Eg increases by 0.6, it is decreased by 0.4. So I can say it is a plus 0.6 into number of Eg electrons, minus 0.4 into number of T2G electrons plus pairing energy. Pairing energy depends on how many electrons are paired up. Got it? So this formula you have to apply for crystal field splitting energy calculation. So let us apply this formula for each case. Here each case, let us apply the formula. You keep it in mind. It is a first T2G1 Eg0. So in the place of Eg0, T2G1, what will come? It is minus 0.4. There is no pairing of electron and its symbol is, units is del O. Crystal field splitting energy minus 0.4, and here also minus 0.4 del O. Now D2 means T2G2 Eg0. So in the place of Eg you can put still 0, and in the place of T2G you can put 2. So 2 into minus 0.4, 2 into minus 0.4, it is going to be minus 0.8 del O, minus 0.8 sorry del O. And same here also, because there is no paired electron, 0.8 del O. Now D3, what will come? You tell me. T2G3 Eg0. So in the place of Ez it is a 0. In the place of T2G you have to put now 3. Now 3. So what will come? It is minus 1.2 del O, and here also minus 1.2 del O. Now difference will come. D4, here strong ligand and weak ligand difference is there. Strong ligand, it is a T2G4. T2G4 means here in the Eg0 and T2G you have to put 4. So 4 into minus 0.4, it is minus 1.6 del O, and one electron is paired. T2G4 means one electron will be paired. That's why I will put plus P. Right, the P value will be given in the question, so don't worry about it. Now T2G5 Eg0, what can I write? In the place of T2G I have to put 5. T2G I have to put 5. So 5 into minus 0.4, it is a minus 2.0 del O, plus this time 2 electrons are paired. This time 2 electrons are paired, so that's why I have to put 2p. Got it? Now D6, T2G6 Eg0. So Eg0, T2G you have to put 6 electrons. 6 into minus 0.4, it is a minus 2.4 del O, plus 3 electrons are paired, so I can put here 3p. So like this you have to complete the table. That's your homework. And here let us do, in the case of D4, what will come? In the case of D4, T2G3 Eg1. So T2G 3 Eg1. So what will come? It is going to be plus 0.6 minus 3 into 0.4 minus 1.2. So it's going to be minus 0.6 del O. Now here pairing is not there, so electron is going as per the Hund's rule, so that's why pairing energy P will not come. And here what will come? D5, you count. Eg 2 electrons, T2G 3 electrons, so which means 0 will come, so 0 del O. And this one Eg 2 electrons and T2G 4 electrons, so 2 into 0.6, it is 1.2, and 4 into 0.6 minus 1.6, so it is going to be minus 0.4 del O. Here electron is not pairing against 2 Hund's rule, that's why the pairing energy will not come. Pairing energy will come only in the case of strong ligands. Got this one? So practice this one, and continuation I will explain in the next video or in the next part. Right, so rewind the video and read it carefully. Thank you guys.
Subscribe now and press the bell icon. Never miss an update. Subscribe now and press the bell icon.